So, hello students. Today we are going to continue our discussion on thermodynamics that we started some lectures ago. So, in the last lecture, we had known about the Born-Haber cycle. I gave you a brief description about the concept of Born-Haber cycle, that it is nothing but application of Hess's law in the case of a solid ionic crystallized compound. So now when we have learned a lot about thermodynamics by this point of time, now we will proceed to a next section when we will talk about the spontaneity of a chemical reaction, the entropy changes of a chemical reaction, and what governs and what detects that whether a chemical process will be spontaneous or not. But before going there, I will give you a short recap and a brief introduction about the Born-Haber enthalpy, Born-Haber cycle and the enthalpy. So in the last class, we started with the Born-Haber cycle. So in the Born-Haber cycle, we took up an example of formation of NaCl from Na plus and Cl minus. So in the last class, what we learned? We learned that when we have a solid ionic compound, that is NaCl, and when we are going from NaCl solid to Na plus gas plus Cl minus gas. And in the cycle, if you remember, I showed you the entire procedure, like what are the steps involved, the ionization energy, the electron affinity, the sublimation process, the bond dissociation process, and whatnot. So in this procedure, we saw that the delta lattice of NaCl, that is a lattice enthalpy, it is around plus of 788 in kilojoule per mole. This was the lattice energy for NaCl. Now, in this case, if we take up this equation, so this is a thermochemical equation, because I have told you what do you mean by thermochemical equation. In thermochemical equation, we have a balanced chemical equation and we have the delta value along with it. So this equation is balanced, and if you calculate the delta Ng for this reaction, so I guess you will be able to tell that what is delta Ng here. We will take up the coefficient of the gaseous components in the products minus coefficient of the gaseous components in the reactant. So Na plus coefficient is 1, Cl minus coefficient is 1, because both are gaseous. And we have the NaCl solid where we have no gaseous component. So delta Ng here will be equal to 1 plus 1 minus 0, which is 2. So delta Ng is equal to 2. So internal energy is only smaller by 2 RT, and it is equal to 783 kilojoules per mole. So now we can use the value of this lattice enthalpy to calculate the enthalpy of solution from the following expression. So what is the expression by which we can calculate? We know that is delta solution of H is equal to delta lattice of H plus delta hydration of H. All are in their standard state. So all have this minus sign that I have not written, because this minus sign is applicable for all these delta H values. Now we have the expression, we have the lattice enthalpy value, which is 788 kilojoule per mole. And we have the delta hydration value from the literature, that is minus of 784 kilojoule per mole, which is known from the literature. So we have these two values. And so if we put this in the equation, we have the delta solution of H is only 4 kilojoule per mole. So this solution of the NaCl is actually accompanied by a very little heat change, because it is actually equal to only this much amount of energy. So the dissolution of NaCl in water, that is delta solution of H, is actually accompanied by a very little amount of heat change. So now we have got a very brief idea about how we can calculate the lattice enthalpy. Also, how we can be able to calculate the delta solution of H from the given lattice energy value and the hydration energy value that will be given to us. So now we move on to the next part, that is the quite important part in the field of thermodynamics, that is the spontaneity of a chemical procedure. So before going to the topic of spontaneity, so we will have a brief recap about the first law of thermodynamics. So till now we have discussed a lot about the zeroth law and the first law of thermodynamics. So it tells us about the relation between the delta U, Q, that is the heat involved in the reaction, with the work done, that is W. So this was everything about the first law of thermodynamics. Delta U is equal to Q plus W, where Q is the heat involved, W is the work done, and delta U is the change in internal energy. So it actually tells us the relationship between the heat absorbed and the work performed on or by a system. But in the first law, you see there is no restriction that where the heat flow will be taking place. So we have a system. In the first law, we have a system. Suppose this is a beaker and it is a system and it is kept inside the surroundings. And so let's say in the system we have some amount of matter and this is the surrounding. But in this case, from the first law, we have been able to see the how much amount of heat is actually flown. But what is the direction of heat flow? There was no restriction. So actually, in fact, naturally occurring procedure that are actually happening naturally in our environment, all these are actually, whether it is chemical or physical, they will spontaneously go to one direction only. So suppose we have a chemical reaction which goes from a state of P from a state of Q. So whether it will go P to Q, whether it is a chemical process or physical process, it will go in a unidirectional matter only. So when it is happening, you say it will be happening in a unidirectional matter. So what are the chemical procedure that I am talking about, the unidirectional matter? Suppose a gas is expanded from a closed container into a very much available molecule. So we had a gas here. Now it will expand to this larger chamber. A gas G was there. Now it will come to this volume. So it was initially at a volume of small v. Now it is expanded to a volume of capital V, where small v is very, very less than capital V. So here a gas is expanded to fill the available volume, that is unidirectional. Obviously, from this left side state of a smaller volume, small v, to the larger volume, capital V, the gas will flow. Also, the burning of carbon in dioxygen will give us carbon dioxide. So whenever we take graphite, for example, in the solid state, and we take up graphite and we burn it in oxygen, and it will produce CO2 gas. So burning of graphite in oxygen to form CO2, all these processes occur spontaneously. All these the procedure are spontaneous. They occur without the help of any external partner or external help because they cannot be reversed naturally. They will perform spontaneously. But heat actually will not flow from colder body to warmer body on its own. Suppose we have a hot body or hot plate, a hot plate it is, which is having a temperature of say 150 degrees Celsius. And we have a comparatively colder plate which has a temperature of, let's say, 30 degrees Celsius. So this is the hotter body, this is the colder body. And heat flow will generally be formed from the hotter body to colder body. So heat flow from a hot body to a cold body is natural, or you can say it is spontaneous. But in case of the heat flow from the colder body to hotter body, you can from colder body to hotter body, the heat flow will not occur spontaneously. So that's why when the gas is a smaller volume, it will expand into a larger volume. So then the process is spontaneous. But the reverse procedure, that is the gas flow from a large volume container to a low volume container, is not spontaneous. So these and many other spontaneously occurring the changes that are happening in our atmosphere are showing unidirectional flow or unidirectional process. Unidirectional means it will specifically occur in one directional actually. So in this case, this 30 degrees Celsius to 150 degrees Celsius body heat flow is not spontaneous, but this is spontaneous from a hotter body to a colder body. Likewise, in case of gas which was in a smaller volume, it will be expanded into a larger volume. That is spontaneous. But the reverse one, where the volume is contracted, the procedure or the process is not chemically spontaneous. So actually, when we have the discussion, you will might have get the question that what will determine the direction of a spontaneous change, which factors will govern the driving force of the spontaneously occurring changes. What are the reason why, or what are the criteria you can say that for the processes whether it will take place or not. So for discussing this spontaneity process, like what is the spontaneity, what are the factors that govern spontaneity of a chemical reaction, we need to understand several parameters, which we will discuss in this section. So let us first have a clear idea about the spontaneity, or what do we mean by a spontaneous reaction or spontaneous change. So it is a spontaneous reaction, and what are the criteria of a spontaneous reaction? So actually, what you can say by your idea, normal idea, that whenever the common observation is whenever some contact is there between two reactants, it will be an immediate reaction. We can take up the reaction of hydrogen and oxygen. So let's say we are taking the combination reaction of dihydrogen and dioxygen to produce water. We have to actually balance this equation. So we'll put a half over here. So this is actually a balanced reaction between molecular dihydrogen and dioxygen to form water in liquid state. Now, these gases may actually be mixed at a room temperature. Room temperature means around 25 degrees Celsius. And it can be left for many years. For many years, it will be kept as it is, but we will not observe any perceptible chemical change. So you can say, sir, as you are showing that H2 gas and oxygen gas, if mixed together in proper quantity, it will produce water. So by this quantity in our lab also, in your room also, we can produce water, because as you know, water is the essential, most essential solvent in our daily life. It is termed as life actually. Without water, we can't even think of a second in our daily life. So if there is a very easy reaction, because H2 is there, oxygen is there, so we will just mix them in room temperature and we will have water. Why do we need to have this purifier and all these things to produce water? This question is very much trivial, but the fact is somewhere else, because this reaction at room temperature does not actually occur. You can ask, what do you mean by does not occur? The rate is actually extremely slow or sluggish in this case. So if we mix H2 gas and oxygen gas at room temperature and leave them without any perturbation or without any disturbance or without heating them, then we will see there is actually or perceptibly no chemical changes occurring, even though years, decades can pass by. But when the reaction is actually taking place between them, between H2 and O2. But the barrier for which they have to perform or undergo the reaction, the barrier is so high. So over the years, it will perform very slowly. So this reaction at room temperature is actually extremely slow. Extremely slow. So it is called, though it is called a spontaneous reaction. So spontaneity means actually it is having the potential to proceed without any assistance of external agency. So now we have got a, a kind of explanation for a spontaneous reaction. So a spontaneous reaction is it is having a potential. To proceed without any external help. Without any external help or assistance. This is over and over a spontaneous chemical processes definition, that it is such a reaction which has a potential to proceed without any external help. So another aspect that we will be having, that in a case of a spontaneous reaction, that we cannot reverse their direction, they cannot reverse their direction on their own. So on their own, they cannot just switch the procedure. So if A to B is a spontaneous process, and how we can say it is spontaneous? Because B to A transformation will not occur by its own help. We have to externally apply some assistance to make the reaction a reversed one. So over and over, we have got overall we have got a definition for the spontaneous process. A spontaneous process is such an irreversible process that may only be reversed by some external assistance. So this is the actual the explanation that we have to have our in our mind, that that is the spontaneous process definition. Since we have learned a lot about enthalpy in our thermodynamics chapter, we have learned a lot about the term of enthalpy, that is H. And in many numerical examples, we have seen this term of delta H, that is change in enthalpy. So now there occurs a question that the decrease in enthalpy, is there any decrease in enthalpy a criteria for spontaneity? Is there any decrease in enthalpy a criteria? So delta H, if it is negative, so our question in this case, that if delta H is negative, that means H2 is less than H1. That means the enthalpy is decreased. So if we examine the decrease in enthalpy is a criteria for spontaneity. So if we examine the phenomena like the flow of water from a downhill or fall of a stone on the ground, we find that there is a net decrease in the potential energy in the direction of change. So we might be tempted to state that a chemical reaction is spontaneous in a given direction because there is a decrease in energy taking place, as in the case of a exothermic reaction. So in exothermic reaction, if you see delta H is less than 0, you can say, like, sir, we have seen many chemical reaction where delta H is less than 0, and these reactions are exothermic because there the net energy is actually decreased. Also, if we have, say, there is a hilltop over here, and we have kept a stone here. And if we put the stone from here in a free fall, it will come down to the ground surface. So it actually shows that it is a spontaneous process, because if we put a stone on the top of the hill and leave it as it is, it will come down to the ground. So in this case, you see the potential energy also decreases. At the ground, the potential energy is actually 0. But at this high altitude, the potential energy was quite high. So if a stone falls from a hilltop to the ground level, the potential energy will be decreased. So you might say that this process is spontaneous. So whenever there will be decrease in energy or enthalpy, you might be tempted to say that, oh, there is a decrease in energy, so the process must be spontaneous. There are also very typical examples in favor of this phenomena. Like you say, we have this equation N2 plus H2 producing ammonia. This is an exothermic process, and delta H for this reaction is minus of 46 kilojoule per mole, which is an exothermic reaction and also a spontaneous reaction. You see here, if you have to balance this equation, we will put a 2 over here to make nitrogens equal, and then we have 3 over here to make this equal. So this is a spontaneous reaction. And also, if you have, we can actually make this by 1 1 also. If we put a 3 by 2 over here and half over here, then it will be NH3. So then 2 will be cut. So now it is also balanced. Half N2 plus 3 by 2 H2 will produce ammonia. And the delta H value is minus of 46 kilojoule per mole. There are other examples in favor of this also. We have the equation half H2 plus half Cl2. It will produce 1 mole of HCl. And the delta H value for this is minus of 92.32 kilojoule per mole. Here also, it is an exothermic process. That's why you might have the assumption that it is spontaneous. The formation of water from H2 as O2, the delta H is also the reaction that I showed you in the first time, like from H2 and O2. Will produce H2, and the delta H value in this case is 2 minus of 286 kilojoule per mole. So you see in the spontaneous procedures over in all these cases, delta H value is actually negative or less than 0. So you might assume the fact that whenever delta H is negative, there will be a net decrease in enthalpy. So the procedure might be, or the process might be, spontaneous. That is decrease in enthalpy in passing from the reactant to the product side is actually may be shown for any exothermic reaction on an enthalpy diagram that I will show you. Thus, the postulate is that the driving force may of a chemical reaction may be due to the decrease in energy sounds reasonable on the basis of these evidences so far. So we have got these evidences so far that the decrease in enthalpy may be caused as a criteria for determining the reaction to be spontaneous in nature. So if we have the following, so we can actually draw a diagram on basis of this. This is the enthalpy diagram for an exothermic reaction. We have two axes. On the x-axis, we have the reaction coordinate. On the y-axis, we have the enthalpy or H that we will calculate. So let's say the total enthalpy of the reactants is pointed here, which we will term as HR. The R stands for the reactant enthalpy. And let's say the product enthalpy stand out here. That is HP. So the energy gap that is involved in the difference between these two, HP minus HR or HR minus HP, is termed as the del RH value. That is the net heat evolved in the reaction. That's why it is negative. So we'll have reaction coordinate, we have the enthalpy, the HR is greater than HP. So del RH is less than 0. So this is enthalpy change for an exothermic reaction. Now let us take up the example of this nitrogen and oxygen forming NO2 gas. So we have taken up this reaction N2 plus O2 producing NO2. So we'll put a half over here for the balancing. So we have half N2 plus O2 producing NO2. The del RH for this reaction in kilojoule per mole in the standard state is equal to plus 33 kilojoule per mole, which is positive. Now, also, we have another reaction where carbon, that is graphite, reacts with sulfur liquid to form CS2. We'll put a 2 here for balancing. The del RH value in this case is plus 128.5 kilojoule per mole. So in the both the cases, you see the del RH value is actually positive. So we have the del RH value in a positive sign. But till now, what we are experiencing, like all the del RH values were negative. That actually gave us some idea that when del RH value is negative, the procedure might be spontaneous in nature. But in this case, these reactions are though endothermic. These reactions are endothermic because here the del RH value are all positive. So in this case, what will be the graph in this case? So if we put the similar graph here, we have the reaction coordinate here. We will have the HP, that is the potential of the products, in a high value, but the potential of the reactants will be in a lower value. So here in this case, HP is greater than HR. But though HB is greater than HR, so this box is for this one. But the delta HR value is actually positive. These reactions are endothermic in nature. So exothermic reactions are spontaneous, that we have understood till now. But aren't also, so generally the question comes that does that mean that endothermic reactions are not spontaneous? If enthalpy change or a decrease in enthalpy is the sole reason for a reaction to be spontaneous, then no endothermic reaction will take place. But that is not the case. There are these two examples and some many more millions of examples I can show you that where an endothermic reaction is spontaneous in nature. So here also, this is the del H value, which is positive here. That is the gap between this HP and HR. So the increase in enthalpy may be presented in this diagram that the product enthalpy is much higher than the reactant enthalpy. So therefore, it becomes quite obvious that while decrease in enthalpy may be a contributing factor for spontaneity, but it is not true for all the cases. So endothermic reactions can also be spontaneous. If endothermic reactions can be spontaneous, in that case, we will have some different parameters that we will discuss here. So now we will move to our next part, that is the part of the entropy. That is the one of the major changes that we will be discussing in this case. So firstly, we will see what is actually meant by the term entropy. So what drives the spontaneous reaction in a given direction? So let us examine a procedure where I have taken two examples where I have shown that either del RH is greater than 0, or I have taken the example where del RH is less than 0. First one is endothermic and second one is exothermic in nature. But what happens if we take that del RH equal to 0? So this section we have not discussed till now. Like what will happen when our change in enthalpy will be 0. So there will be no change in enthalpy, but still the process might be spontaneous. So let us consider a diffusion of gas into each other in a closed container that is isolated from the surroundings. So we have two gases, gas A and gas B. Now they are represented by this diagram that I am going to show you. Let's take a box. So we have a box which in the middle part has a separation. We have this box in the middle part, we have a separation, and in this separation case, in the left chamber, we have the right chamber. So we will term this chamber A, and we will term this as chamber B. So in the left hand side, let's say there are this gas where I am putting the orange lines. Orange dots are actually represented by the orange gas molecules, which let's say as a gas. And on the right hand side, let's say the gases are actually represented by blue dots. So these two are actually different gases. So on the left hand side, we have these red dots or orange dots of gas A. On the right hand side, we have the blue dots indicating the presence of gas B molecules. Now, they are separated by a movable partition. So this is the separation between them. this green window, which is a movable partition. Now, when this partition actually moved away or withdrawn from the system, then these two gases, this gas red and gas blue dots, so A and B gas will start to mix, or you can say diffuse between one another. After a period of time, the diffusion will be completely complete. So, as you can say, after some time, this diffusion will be complete. And then what will be the scenario here? So now in this case, we will altogether have all the gas particles mixed. And this mixing will be completely random between the gas molecules. These Brownian motions will completely be random, and we do not have any control over it, how the gas molecules will be mixed. The mixing between two gas molecules will be completely random, like this. So from this state, A and B gas were separated by a movable partition. And now, whenever we have lifted off the partition, the gas molecules are actually mixing with each other. So we have to first examine the process before partition. If we were to pick up the gas from the left side of our container, let's say the gas A, we'd be sure that these molecules will be gas A. And similarly, if we were to pick up the gas molecules from the partition number B, that is the right hand partition compartment, it will be obvious that we will be picking up gas molecules blue. But now, after we have completed the mixing between these two gases, now we have to pick molecules from the container. Whether the molecules are picked or of gas A and gas B, we cannot say. But we say that the system has become less predictable or more chaotic in nature. So here in this case, if I have to randomly tell you that pick one gas from this gas mixture, and randomly if you pick, you cannot be 100% sure whether the gas is blue or the gas is red. So that means in this case, whether it is A or B, the system has become less predictable. And less predictable means it has become more chaotic. So this state that we have got over here, it is more chaotic in nature. So on the right hand side, we have a more chaotic but less predictable kind of system. So we actually may formulate another postulate here that whenever a system is isolated in nature, there is always a tendency for the system's energy to become more disordered or more chaotic. And this could be a criteria for a spontaneous change. So actually a system itself, the system's energy may become more much disordered. So is disordered. See, disordered nature actually may lead to spontaneity of a chemical reaction. So more disorderliness or more chaoticness may actually be a criteria for the spontaneous chemical change. So at this point, we may actually introduce a term that is called as entropy. That is very much important. So after we have discussed all these conceptual parts over here, I guess you have known a brief about what I am trying to say. The entropy terms actually helps us to denote the randomness or the disorderedness of some particles in a specific isolated system. So now we move to the connection of the entropy and the spontaneity. So in this quest, we have to identify a property that may reliably predict the spontaneity of a process. And that's why we have actually introduced the term, the thermodynamic function that is called entropy. And it is denoted by the term capital S, which is known over here. Processes that involve a increase in the entropy of the system. That means whenever randomness is increased, then it is called the delta S system is greater than zero are very, very spontaneous. However, there are examples that show contrary. You might actually plunge out that whenever sir, that means in delta S is less than zero, that means the procedure won't be thermodynamically spontaneous. No, that is not the case. Here also, these two terms will actually be helpful. So actually, for calculating the spontaneity of a reaction, H, that is the enthalpy, and S, that is the entropy, both these terms are useful. I cannot solely say that whenever the enthalpy is negative, the process is spontaneous. I cannot solely say that whenever the entropy is positive, the process will be spontaneous. Both these terms, H and S, contribute equally to the spontaneity of a system. And if or whether we have to predict what is the spontaneity of a reaction, whether it is spontaneous or not, both actually will be governed only when we will calculate the enthalpy change and also the entropy change. But actually, this entropy is a very promising candidate to actually determine the spontaneity of a chemical procedure. By expanding the consideration that the entropy change includes in the surroundings, we may reach a significant conclusion that the relation between the property and the spontaneity. But in case of thermodynamic models, the system and surroundings compromise everything. That is the universe. So the change in entropy of the universe is actually summation of the change in entropy of the system and change in entropy of the surroundings. That is actually shown here. So delta S universe is equal to delta S system plus delta S surrounding. Now, for illustrating this relation, we have to consider the process of heat flow between two subjects. One identified will be with the system and the other will be taken up as the surroundings. But before moving there, we have to have a brief idea on entropy too. The, the, the mentioned disorder is the manifestation of the entropy. So this disorderliness that I discussed in the last slide, this disordered nature or the chaotic nature, it is nothing but the manifestation of entropy. To form a mental picture, you can think the entropy, but if you have to think inside your brain, like what is meant by entropy, like you can say that it is a measure that will be measuring a degree of randomness or disorder in the system. The greater the disorder in the isolated system, the higher will be the entropy. And the higher will be the entropy, the more spontaneous the reaction will be. So entropy change can be attributed to rearrangement of the atoms or the particles that are present in the system. And if the structure of the products is very much disordered, then that of the reactants, there will be a net increase in the entropy. Suppose we have products where the particles are very much disordered than that of the reactants, then it will be resultant increase in the entropy. The change in entropy that is accompanying a chemical reaction may be estimated qualitatively also by a consideration of the structure of the species that is taking part in the reaction. Now, decrease in the regularity of the structure would mean the increase in entropy. For a given substance, you know that a crystallized substance, a crystal material, is the lowest entropy state because it is the most ordered one. You see, in a crystal structure, there will be ordered array of atoms. Suppose this is the crystal lattice, and we have many atoms placed inside the crystal lattice. One over here, let's say another over here, another over here, another over here. And let's say other atoms are actually situated on the other parts. One atom is here, another here, another here, and then another here. And let's say another particle is actually sitting in the middle. So this you can say in a crystal lattice structure, it will be the lowest entropy state because it is the most ordered state. All the atoms are actually in a specific position, and that's why in a crystal structure it is the lowest entropy structure. And likewise, you can say in case of a gaseous system, the entropy will be highest because in gaseous case it will be much more random. The gas molecules will fly from here to there to and fro heavily. Now, how we can calculate the entropy on a quantitative basis? So, quantitatively, we can also calculate the disordered nature or the chaotic distribution of energy among the molecules. So, entropy, like many other thermodynamic property, such as internal energy, as you know, internal energy, or as you know, the enthalpy. In case of entropy too, it is a state function, and that's why delta S is independent of path. That is, change in entropy is independent of path. So whenever heat is added to a system, it will actually increase the molecular motion because the energy will be increased. Whenever we are putting some energy, the heat energy of the molecules will increase. That will increase the randomness in the motion of the system. So Q has a randomizing influence on the system. So can we actually equate delta with S with Q? So I am saying that whenever I am giving some heat or providing some heat to the system, the randomness of the particles will increase. That will show that the randomness will be increasing. So does that mean that delta S and Q are equal? Because if we are producing heat to the system, the randomness will increase. So there is a very much significant connection between Q and delta S, but they are actually not equal. Delta S is not equal to Q. It is obvious that Q has a very good randomizing influence on delta S, that is the entropy. But the distribution of heat also depends on the temperature at which the system is present. So a system at higher temperature has greater randomness in it than the one at lower temperature. Then actually temperature is the measure of average chaotic motion of the particles present in the system. So heat added to a system at a comparatively lower temperature can cause a greater randomness in the quantity of heat. Just suppose you have two bottles. One has a temperature of 20 degrees Celsius water, another has a temperature of 100 degrees Celsius water. Now, if we add some specific amount of heat, let's say Q amount of heat or 100 kilojoule of heat to both of the bottles, one having 20 degrees Celsius water, another having 100 degrees Celsius water. By your common sense, you can say that 20 degrees Celsius bottle will be having much more randomness because the temperature change will be much higher there. So the heat added to a system when the system is a lower temperature will cause a great randomness. So delta S is actually related to both Q and T. With Q, delta S is actually proportional, and with T, it is actually inversely proportional. And that's why the objects at different temperature, it will flow from the hotter to the cooler object. So for delta S system, we have the equation that is delta S system is minus of Q reversible by T system. So delta S is actually Q by T. The total entropy change, that is delta S total for the system and surroundings of a spontaneous process, will be given by delta S total is actually greater than 0. So when a system is actually in equilibrium, the entropy is maximum and the change in entropy, that is delta S, will be equal to 0. Delta S will be equal to 0 when the system is in equilibrium. So till now we have reached a point that delta S system is equal to Q reversible by T system, and delta S surroundings will be Q reversible by T surrounding. Now the arithmetic signs of Q reversible denote the loss of heat by the system and the gain of heat by the surroundings. Now we know that T system is actually greater than T surroundings in the scenario, because heat flows from the hotter to the cooler object, and this always observed naturally or spontaneously. Designating the hotter object is the system and invoking the definition of entropy. Let's say hotter object is the system. So from system to surrounding, it will flow. And that's why T system is greater than T surroundings in this scenario. The system is hotter. So the magnitude of the entropy change for the surroundings will be greater than that for the system. So the sum of delta S system and delta S surroundings will yield a positive value for the delta S universe. This process involves an increase in the entropy of the system. So as you can see, Q reversible is in both the cases. And so if I put this mathematically over here, in this case, we have delta S system. So delta S system is actually Q reversible by T. And delta S surroundings, since this much Q reversible heat is taken up by the surrounding, it is minus of Q reversible by T of the surrounding. This is T of the system. And as you know, T system was the hotter one, system was hotter and surroundings was colder. So T system is greater than T surrounding. So if we calculate the delta S universe over here, it will be delta S system plus delta S surrounding. So it will be Q reversible by T system minus Q reversible by T surrounding. So if we take Q reversible common, so we'll have this 1 by T system minus 1 by T surrounding. So now we have got the equation that delta S universe is actually equal to Q reversible 1 by T system minus 1 by T surrounding. So as we move this equation, the arithmetic sign of Q reversible denotes the loss of heat by the system and the gain of the heat by surrounding. In this system, T system is greater than T surrounding. So in this case, the sum of delta S system and the delta S surroundings, what will be equal? So actually here in this case, since Q was actually given by the system, Q was heat released, so it was minus. And since heat was taken by the surrounding, it was positive. So if we see, if you have to take Q reversible as negative, we will have the equation. It is T system minus T surroundings. So if we put the values over here, you will see T system was greater than T surroundings. So 1 by T system was less than 1 by T surrounding. So if it is negative, this negative and this negative, will be equal to greater than 0. So delta S of universe is actually greater than 0. So for this case, the entropy change is actually positive. So likewise, we can take up multiple examples where we can see that the entropy change will be accompanied and it will be actually greater than 0. That means it is a spontaneous process. So with this, we will conclude today's class. But in the next class, we will deep into more details of an entropically favorable process, and we will see some numerical examples where you can be able to calculate the delta S for a system. So if you have any doubt regarding any of the slides, you can go ahead and ask.